We are live, 2 o'clock Brisbane time, 3 o'clock Sydney time. Hi everyone, this is the second webinar from the ACIGS, Australasian Chapter of Geosynthetics Society. So we have Warren Hornsey talking to us today. I just thought as an intro, we'll just take a couple of minutes to show you how to access the journals, the two prestigious journals that IGS is publishing. So we talked about the IGS, the Global International Geosynthetics Society, and then where the Australasian chapter sits. We also talked about some of the benefits of being a member of ACIGS, and as part of those membership benefits, you get free access to two journals. One is Geosynthetics International, and the other one is Geotextiles and Geomembranes. So the process is pretty simple. You just type in geosyntheticsociety.org, and that gets you to the IGS website, which looks like something like this. And then there is a members section that you can, I'm just trying to find my laser point. So that's the members login. So you put in your username and password to log in with your membership details. If you are a paid IGS or ACIGS member and you still don't have your username and password or your IGS number sorted, please contact us and we can organize that for you. Then once you're logged in as a ACIGS member, you go to this technical resources tab, and then you click on that little arrow and it gives you an option to access the journals. So like I said, two journals that you can access for free using your IGS membership, Geosynthetics International and Geotextile and Geomembranes, are the two tabs that you see here. So you click on the tab that you want to access the papers, and then here is the IGS member access. And it's got a link here that gives you direct access to IGS journals. When you click on that, it takes you to ICE Virtual Library website, and you will see up there that your access is provided by International Geosynthetics Society. So this one that I've chosen here is Geosynthetics International. So you just scroll down and basically find your paper that you want. There are papers from 1994, I think, on this one, and 1980s for the other journal that you can access. Normally 5 to 6 issues every year is published by each of these journals, and it's including state-of-the-art papers and research that is happening in the geosynthetics world. So today's webinar, like I said, we have Warren Hornsey talking to us about geomembrane liners and measurement of the strains. So we thank TRI Australasia, who is our sponsor for today's webinar. So the topic is Geomembrane Strain Measurement and how this applies to Cushion Geotextile Design. Just a brief introduction of about Warren. He is a professional civil engineer with experience in Africa, UK, and Australia. He is the director of TRI Australasia, an independent geosynthetic testing and analysis laboratory based on the Gold Coast in Queensland. He is directly responsible for all geosynthetic testing and support in the Australasian region. His current role means he is involved in landfill quality assurance on a daily basis and has strong relationships with regulators, designers, and manufacturers. He has 22 years experience in geosynthetics design, manufacture, and R&D. He is currently a committee member of the International Geosynthetic Society and was previously chairman of Standard Australia CE20 Committee on Geosynthetics. He has published over 25 peer-reviewed papers covering a range of geosynthetic application and has a passion for all things geosynthetics related. Thank you. And I'll hand over to Warren for his presentation. Just for a moment, because I have to give my chair to Warren. He's just right next to me now. I go to there. That is? That's it.
All right. Good morning, good afternoon, good evening to everybody that's signed up for the presentation. I hope you find this presentation interesting. To give you a bit of background, my first paper on geosynthetic lining and protection was back in 1999, so I've been doing this for a fair while now. So I have a fair bit of experience in this, and what I'm going to present on today is my experience of working with these materials over the years. So essentially what we're going to talk about in this presentation is the geomembrane strain measurement and how this applies to Cushion Geotextile Design, and we'll work through that as we go through the presentation. One of the most important things to realize with this sort of work is that we don't live in a perfect world. So when we do testing, it's very difficult to make things match the real world exactly. So we have to compromise in some areas. Very few tests mimic field conditions perfectly. There's some areas where they overstress materials, there's some areas where they understress materials. So you just need to know what the limitations or the effects of these tests that you're doing and how to apply the results that you get from those tests to the real world. The area that we need to understand is that these polymers are relatively new in terms of general materials that are used in construction. So polymers used for geomembranes are continually being upgraded and improved. Geotextiles, there's a lot of R&D that goes into those sort of materials. So it's not a fixed position that we come from, that these materials are changing all the time, and our designs and our testing need to allow for that change in methodology and materials. So in terms of the presentation, what we're going to talk about is HDPE characteristics, because this is primarily what we're looking at is HDPE. We're going to look at the European versus the American test methods and philosophy in terms of allowable strains. We'll go into a lot of detail in terms of method comparisons, so that when you're doing a design, the results that you get are not so much, are very much related to the test method that you've used. So if you use different test methods, you will get different answers. And it's really important for the designers out there to understand when they get a strain measurement exactly what that means. Then we'll look at geotextile specification in terms of what is important when you're specifying geotextiles for protection, and then going into conclusions about what you need to know when specifying strain values, and then what the magic numbers are. And to be honest, I've gone out on a limb here, and this is something that some people are going to like me for and some people are not going to like me for, but it's just a number has to be put down, and that's what I've attempted to do at the end of this presentation. So in general, what we're talking about is in liner systems is a HDPE base liner, which is overlain by a geotextile that provides protection from the drainage gravel which is laid across the top of it. And what you can see in these slides is a typical example of a very relatively large dozer spreading drainage gravel across the geomembrane protected by a thick non-woven geotextile. And when it works properly, it works really well, but then you see the bottom two slides, and that's when it hasn't worked terribly well, and there's holes punctured in the liner. And that's really what we want to avoid. In fact, the designs that we're dealing with is staying well away from puncturing, and we'll go into those details. And it's more about the indentations and the very limiting strains within the geomembrane. So once it's got to a point where there's punctures knocked through the geomembrane during installation of the drainage gravel, you're in real trouble. Just from a practical point of view, protection geotextiles are not new. They've been around since geomembranes were first used. There are multiple inputs into how well these materials work, from the manufacture of the geotextiles through to the quality in the manufacture of the geomembranes. As stated previously, the test methods vary, and we'll go into the details of those, and the analysis techniques within those test methods also vary. And you as the end user need to understand what those variables are. So from a strain perspective, and that's what we're going to talk primarily about today in terms of these geomembranes, it's not about puncture, it's about strain on the liners. There's an example with exactly the same rock profile with two different tests carried out. The slide on the left is a profile that is left when we've had no geotextile protection. In other words, the geomembrane is placed directly against the rock, and you get a very distorted profile. And the one to the right is where there's a 1600 gram geotextile placed against this, between the geomembrane and the rock profile, and loaded to 600 kPa. So you can see the effect of how the geotextile reduces the indentations and therefore the strains on the geomembrane. In graphical the images of those, so that was the real aluminium plates. Part of the testing that we do primarily here in Australia is doing the laser scanning techniques, which we'll talk about later. What you can see is the relative strains of those two. No geotextile protection over here. Now, just Simek, how do I get that little laser? Okay. Thanks. Sorry about that, guys. So what you can see here on this image is large areas with red areas, which are showing areas of greater than 3% strain, and then small areas within that are circled in white, which is areas exceeding 6% strain. By just including a lightweight, and in Australian and European terms, a 370 gram geotextile is a lightweight geotextile into that profile, that you can significantly reduce the strains occurring within that liner. If we graph this somewhat differently, what you can see is, as where we've done the comparison here between a geomembrane with no protection at 600 kPa, confining pressures with strains exceeding 25%. You include again, lightweight geotextile into that mix, and it significantly reduces the strain values developed down to around the 12% mark. Now that's a big difference. As you reduce the loading placed on the geomembrane, the strains are reduced, but so too the influence of the geotextile. So the smaller the lower the loads, the less impact the geotextile has on it. But in all cases, the inclusion of a geotextile improves the performance or reduces the strains on the geomembrane. And for us, it's working out what are the maximum allowable strains that should be out there. and which geotextile provides the best protection for your application. So in terms of testing itself, the results depend on variables which are built into the test. The size of the gravel, the shape of the gravel, the geotextile itself, how strong it is, and we continually use mass through this presentation, and I'll show you a little later that mass really isn't the good measure of how to define a protection geotextile. It's just an easy way of defining things, a simple way of doing it. The other area that's important is the subgrade, whether it's rubber or clay, or whether you include a GCL, and then it's whether the GCL is hydrated, and then it's how much hydration you have on that geotextile. So whether it's hydrated to 50% moisture content, or is it to 150% moisture content? All of those factors influence the results. The other area that's important is where the recording plate is placed in the structures. So in other words, is it below the geomembrane? Is it above the geomembrane? And that also has an impact on how what strains are developed. So in terms of good science, in terms of being able to compare things without accurately, you want to limit those variables. And some of the tests that we do try to do that as best we can. So from a purely materials point of view, understanding the HDPE characteristics is important to understanding what we're measuring at the end of the day, and how the strains impact this material. So what we're going to look at are the standard sort of tests that you would do for a geomembrane, so tensile strength, puncture resistance, and this is rod puncture resistance, and CBR, which is generally used for geotextile testing, but is relevant for what we're talking about, because we tend to talk about gravels that are around the 50 to 25 millimeter diameter, and then stress crack resistance, which is one of the key factors. So if we talk about tensile strength of HDPE, it's important to understand exactly what we're testing, because we talk about strength in terms of newtons per millimeter and kilonewtons per meter and so on. Essentially what we have is a dog bone sample that is only 6 millimeters wide. We put it in the tensile machine, and that stresses at 50 millimeters per minute, and what we get is a yield point that's between 12 and 18% elongation, or 4 to 6 millimeters deformation. And that's the typical stress strain curve for a HDPE, and you can see a defined yield point. It then gets into strain hardening and then reaches a peak, and it breaks at that end there. The zone that we're talking about for our analysis is essentially in this yield zone. So that very sharp curve that you're seeing there, when we look at it just on its own in terms of yield, we can see the strength of the material up to sort of 40 newtons per millimeter, and the strain ranges are in the yield occurs at a 12 to 18% strain, or when you're talking about millimeters, 4 to 6 millimeters of deformation, then yield begins in that zone. When we talk about rod puncture, this is a 5 millimeter diameter probe pushing through a geomembrane that's clamped to a 50 millimeter diameter, 45 millimeter diameter hole at 300 millimeters per minute. So it's really quite a fast test for HDPE, and yield comes at 7 to 8 millimeters. And you can clearly see the puncture hole that's created by that hole. What's important to see is that while yield occurs at that 7 to 8 millimeters, it only really punctures at around about 27, 28 millimeters puncture depth. So there's a difference between yield and actual puncture. And that becomes important when you see later how the Americans analyze it. When we look at CBR Burst, it's a 50 millimeter probe the geomembrane, the geotextile, is clamped in a 150 millimeter hole, and the strain rate is 50 millimeters per minute, and yield occurs at around 25 to 30 millimeters depth into the material. Again, you have the strain hardening that occurs after that, before punctures occurred. And the picture that you see over here is a HDPE that has gone beyond yield and is in this zone of strain hardening right now. Now it hasn't punctured as yet. So and I've cut the graph off that that indentation was around 150 millimeters deep. So no puncture had occurred, and yet it had elongated by about 150 millimeters. The stress crack resistance test is a very small dog bone, and the test requires a 20% of the thickness of the material notch to be cut into the sample, and a load of 30% of the yield stress applied to that sample, and it's then left in a heated bath at 50 degrees Celsius with a solution that essentially pulls all the antioxidant package out, all the plasticizers out of the geomembrane. So it's an accelerated test. And what you see in the image on the right-hand side here is the difference between a normal tensile dog bone and a stress crack resistance dog bone, which is significantly smaller. So you're looking at a very small area. So very small changes can make an impact on the results. The other thing to notice is that over time, as polymers and requirements have changed, so has the stress crack resistance of our geomembrane. So back in 1997, GRI GM13 had stress crack resistance of over 200 hours, where the BAM, which is the German requirement, was at 1999, was also around 200 hours. Those have increased to a point where now GRI GM13 is at about 500, is 500 hours, and the BAM regulation is greater than 400 hours. So what I'm seeing in the marketplace is that the performance of the geomembranes has increased. So performance in terms of stress crack resistance has doubled, at least doubled. But I'm seeing more and more in terms of markets where the allowable strains is being reduced, and those, I think that's the major conflict in the industry at the moment, is trying to pull those two things together. Now, this is really important in terms of the philosophy, in terms of European and American standards. And in this presentation, I'll probably offend both sides of this argument, in terms of the Europeans who talk about strain limitation, and they want strains as close to zero as possible, and they use 2,000 to 3,500 grams per square meter geotextiles. To the American philosophy that talks about puncture limitation, they don't want puncture occurring in their geomembranes. Strain is not an issue, and they use very light geotextiles, 250 grams to 400 grams in those sort of applications. Now, it's important to note that there's different resins used in these different zones, so that can play a factor. And while I work for an American company, I tend to go for the European standards more than the American standards. So, but we'll talk about that more as we continue. These are the test methods that are available. EN 13719 is the protection standard for the European standard, and then the British standard, which is LFE, which is the environmental agency standard, almost identical to that test method. Those are the two European standards, and then ASTM D5514, which is the American standard for liner protection testing. And we'll go into detail about these standards. So in terms of the European method, it's essentially a cylinder test, 300 millimeter diameter cylinder. It has a rubber base on the bottom of the apparatus. It uses a 1.3 millimeter lead recording plate to record the indentations. There are 5 indentations are measured. The worst 3 are recorded, and readings in terms of strain are every 3 millimeters, and we'll go into a little detail in that. The advantages of this method is that it allows the influence of subgrade to be assessed, and the loose gravel layer allows deformation of the drainage aggregate to occur. One of the limitations, however, is that the profile changes with each test. So you don't know whether you're testing the performance of the geotextile or the different profile that's been placed by the stone. The other area is the rubber subgrade, whether that's actually equivalent to a compacted clay liner or not. It is also quite a small area to assess, particularly when you're talking about 50 millimeter gravel, a 300 millimeter diameter. It doesn't take many 50 millimeter samples to fill up a 300 millimeter specimen. There is a limitation in terms of selection of the points to be analyzed, and then there's only a limited number of points measured. This is an example of the same gravel tested 3 times using the British or the European standard. And what you can see over here is on the left, we have areas of relatively high strain and areas where there's limited strain on the geomembrane. And when the analysis carried out, strains of 13.97%. The middle one, a lot better distribution of strains of high zones of strain and a maximum strain of 9.98. And then in this last one, very heavily weighted to one side, areas of high strain, high load, with the maximum strain of 15.5%. So there's about a 5% difference in strain, with all the parameters being the same except the gravel profile. So it's very difficult to make educated scientific decisions based on results like that. You have to do an inordinate amount of testing to get a trend out of something like that. The other area where there's questions about whether it's suitable or not is the rubber subgrade, which is 25 mils thick. It has a shore hardness of 45 to 50, 55, shore hardness A. And that's similar to a car tire. A car tire runs from about 55 to 65 shore hardness. And the question is whether that is actually representative of compacted clay liner that's used in the landfill application, particularly when the compacted clay liner is placed at optimum moisture content plus 2%. The next area is looking at how the selection of the worst 5 areas. So it becomes quite subjective from a testing. The person that's testing it chooses the worst 5 indentations and how they select those 5 indentations in terms of measuring it. And you can get an idea of this plate over here, which has, using the laser scanning technique, had 3.2% strain, but how would you choose which one is the worst of those indentations to measure, and how do you record it? Again, this is really important to understand this part of the data that you will get from the European method in terms of how strain is defined. They define strain in 2 ways: local strain, which is essentially the length of the indentation divided by the deformed shape of the indentation. So it's an average strain over the full length of the indentation. The second one is the incremental strain, where essentially you use a straight edge. You measure every 3 millimeters down, you measure the depth, and then can measure the difference in length. And it's the incremental strain over 3 millimeter spacing. So this strain is essentially a localized strain, and this is a global strain type application. So this is really important when people talk about a 0.25% strain. It is essentially an average of all of those strains. It's the local strain and it's the average of all those little individual strains across the cross-section. And in Europe, the incremental strain is restricted to 3%, while the local strain is restricted to 0.25%. In terms of the American standard, essentially it is a 450 diameter cell. The profile is inverted. In other words, the gravel is at the bottom. You have your protection geotextile above the gravel, and then you have your geomembrane above that, and the air pressure comes from the top, and it is placed, that's how you apply the pressure on the system, is through air or liquid from the top. And a 0.5 millimeter organ pipe metal is used to record the deformations. In terms of advantages, it's simple assembly and repeatable testing. Limitations, the placement is not equivalent to the site. It's not because you're placing with the gravel facing upwards. There's no influence of the subgrade. And really the strain calculations that are listed in the standard are just terrible, to say the least, and wrong in most cases. So if you're going to use this method, don't use the strain method calculations that they use there. They are very limited, and the way that they're written is not ideal. In terms of what we do here in Australia, and this is where we take the American standard and have altered it to optimize the testing that we carry out. We use a 0.3 millimeter aluminium sheet to record the strains. The problem with the lead sheet is twofold. A, it's flexible, so when you lift it out of the sample, it's very difficult to retain those deformations to measure. And B, it becomes a environmental issue in terms of getting rid of lead. Throwing away lead is not an ideal solution out there. So we've gone down the route of using aluminium, a very thin aluminium, and what you see on this graph down the bottom here is the stress strain curves in a CBR application of an aluminium versus a 2 mil HDP, and until about 10% strain, they almost sit on top of each other. So there's very little difference between aluminium and HDP up to about 10% strain. After that, HDP gets a little bit stronger and the aluminium gives less resistance. So we're comfortable with running with that aluminium. We also scan it using a laser scanning technique, where on a 450 diameter plate, we'll put 200,000 points, each with an X, Y, and Z coordinate. So we get measurements in terms of height variation of 0.009 millimeters. And we remove the outer edge of that scan so that we're not getting we're taking out edge effects. So essentially the whole surface of your profile that you measure is covered in 1 millimeter squares, and the average height of each of those 1 millimeter squares is assigned. And then the relative height and strain between the neighboring 8 points is measured. The highest strain achieved for any one of those 8 points is then assigned to that 1 millimeter square. So we can work out the areas where large strains occur. And that way, we developed this methodology so that we could analyze the whole plate, not just three or five individual points. It had to be the whole surface area of the plate. And what you can see from that is that you can get a graphical image of the strain values where multiple points, and this is shown by color coding, so red areas define areas of strain which exceed 3% strain, and you can see there's multiple areas around the plate that exceed 3% strain. And then within that, there's little white lines that you can see over there, and those areas are where the strain exceeds 6%. So within a strain image, you can really fine-tune your analysis, and you can work out how many points exceed 3 or 6%, and really understand the whole profile rather than individual points. That then can get placed on a graph so that you can see as a percentage of the total area of that specimen tested, how much of the area exceeds a certain percentage strain. Now, we chose the 1 millimeter grid because at this time when we were doing this analysis, the computer power that you needed to run at a 0.5 millimeter grid meant that the test would run for hours, or the analysis was going to run for hours, and it became very expensive to do. So we stuck with the 1 millimeter grid, not because of any scientific reason other than that the computing time to do the analysis was going to take too long. These days, with computer technology moving on, we probably could reduce it to 0.5 millimeter squares and do it at the same sort of price, but that's just the way we started the testing at 1 millimeter squares. So from there onwards, the other area that we found was to fix the gravel profile so that we could get repeatable testing. So if we tested a gravel with 10 different geotextiles, we knew exactly what the geotextile was doing. It wasn't the gravel profile that was influencing it. We do both testing in the inverted profile and as built, where we flip it over and we have a subgrade, either with a GCL or a compacted clay liner. So in terms of gravel placement, from a practical point of view, we noticed that when gravel was pushed out during the construction process, that the gravel tended to fall with its flat sides down, which left the pointed sides up and exposed to the geomembrane. So any testing that you do with the geotextile or with the gravel paint facing upwards creates a very aggressive profile compared to real life, which is fine if you're using the American method where they want to puncture the geomembrane, I guess. So that's why the geomembrane, the USA uses the inverted profile with the loose gravel profile, because they're trying to puncture the geomembrane. That's what they want to do. When we make up gravel pizzas, we try and get the gravel to fall like it would do on site, and then we fix it in place with the resin. So that gives you an idea of what a gravel pizza would look like. It's made out of multiple layers of resin. If you pour the resin in too fast, it shrinks and it puts a curve in the surface of the rock, and that curve, when we measure it 1 millimeter squares, actually shows up as strain. While it's not strain, it's just a natural curve of the geomembrane due to you pouring the gravel incorrectly. So that's a key thing to make sure you get right. We make this by pouring a silicon layer in the base of a cake tin, for want of a better word, and then removing that silicon after the resin is poured, and we grind out any resin that has filled any of the voids between the rock. One of the concerns is that the fixed profile doesn't allow the rock to move. But again, we're trying to limit the number of variables that go into the test. What's important about this method is what you can see is that the top surface of that gravel is level and straight, and that the voids between the rocks are at least the thickness of the geotextile that you're using to provide as a protection layer. So it's not built, the geotextile isn't supported by resin within the rock profile. we've been doing a fair bit of testing with compacted clay liners of late. And the important thing with this is the moisture content, particularly with sensitive clays, high swell clays. 1% variation in moisture content can have a significant effect on the compressibility or the deformation of that clay. So we've done a lot of testing with this and played with moisture contents. We like to compact the clays as close to as possible to optimum moisture content. Otherwise, they become too soft and too pliable when testing gets carried out. Essentially, we compact it similar to what we do in a CBR compaction process, where we do 3 lifts of 25 millimeter layers, and we compact a 600 millimeter diameter disc to create the compacted clay liner. One of the concerns and limitations with the compacted clay liner process is that you're essentially applying the final load on an unconsolidated clay, which is not what's going to happen in real life, where every day or every week you're going to have a slight increase on load by waste placement, and it gives the clay chance to consolidate and to squeeze out any excess moisture out of the system. With the way that we do the testing at the moment, there's no drainage path for that water to flow, and because we load it up so quickly, there is no time for the water to escape, so we have a relatively plastic clay liner in place. And just to give you an idea of what influence the subgrade can have on the results, what we showed graphically was the difference between exactly the same rock profile with inverted versus with the clay liner below it. And at higher strains, the difference is larger. At lower strains, the difference becomes less. So the lower your strains are, whether it be via pressure or via the size of the rock, the less the influence of the subgrade is. However, it still is important. The other one that we've been looking at is GCLs, and we've been testing with different hydration levels of the GCL. So hydrating the GCL under 10 kPa for 24 hours gives you moisture contents of greater than 100%. Essentially, it turns the clay inside the GCL into a toothpaste. It's literally the feel of toothpaste, and when you load it up, it squeezes all the clay out of the edges of the GCL. If we put it under 24 hours at 25 kPa, it doesn't have as much moisture content in it, but it is still soft and pliable. So when you push it between your fingers, you can squeeze the clay and squeeze it out of its natural position. The most success that we've had with GCLs is when we actually take a sample and we add 50%, we add enough to make it 50% moisture content. You get a firm subgrade, more like what I've seen when we've done exhumations of GCLs that have been under some sort of confining pressure. So, in terms of the results comparisons, the European method looks at a single worst indentation, essentially. It doesn't allow for bending strain. The Australian method, where we use the laser scanning technique, uses a cumulative area, so there's multiple indentations that are added up to create the maximum strain, or strain area. And it also doesn't allow for bending strain. One thing is clear with all of this: the lower the numbers, the lower the differences between these methods. So when we're talking about 16% strain, there are big differences between the European and Australian methods. As you get to smaller, down less than the 1% strains, there is negligible difference between the two methods. And this gives you an indication of what we're talking about here. Is there's a simple indentation that has been measured using the 1 millimeter spacing versus the 3 millimeter spacing. And if we go down at the 2% strain using 1 millimeter spacing, you'll probably be measuring about a 0.5% difference in strain measurement. So the 1 millimeter spacing will result in slightly higher strain measurements. As that strain gets bigger, the numbers get bigger, so 4.6 versus 3.8, it's about 0.8%, and then we're going up to about 0.9. What you've got to be careful of with all of this stuff, don't do percentages on percentages. So there's a 0.5% difference in strains here, but if you take 2.1 divided by 1.65, it's about a 30% difference. So don't do percentages on percentages. It's not a good way of looking at results. Look at it as in terms of there's a 0.5% difference between the results in terms of the two methods that are tested here. In terms of test specification, and this is open to interpretation. The UK method has very strict guidance on what should be put into the test. I'm not convinced that's the right way to go, and everybody's allowed to have their own opinion for it. But essentially what we know is that in my opinion, you should be using the design height. If you double the load on the system, you will double the strain. We've done enough testing to know this, that as you increase the load, the strains increase. So if you double the load, you double the strain. So that's important to understand. Use accurate waste densities. In my role as testing these materials, we see a huge range of waste densities being used. Anywhere from 1 ton per cubic meter to 2 tons per cubic meter. That has a huge impact on the design loads that you're going to use, and then the resulting strains that you're going to achieve. The duration of the test. A few years ago, we did a lot of testing on this to understand the difference between running a 1 hour test, a 2 hour test, through to a 100 hours test. I believe that a 24-hour test is suitable. If there is a slight difference between 100 hours and 24 hours difference in strain, but it is not that significant. The other area is temperature. And the temperature, the UK standard requires extra load factors to allow for temperature, but it doesn't allow for stress relaxation. And I think that as a designer, you should take into account that over time, HDPs will stress relax, and you need to be aware of that. And if you only allow for temperature and not for stress relaxation, you're over-designing your materials. So, and I see I'm running close to time here, so I'll keep moving. In terms of geotextile specification, while we've talked about geotextiles in terms of mass per, or grams per square meter, what you can see from this chart in terms of geotextile masses going up and strains going this direction, the relationship is not very good, with an R-squared value of about 0.5, which is not very good in terms of identifying what truly works with the material. What we can see is that there's a slight improvement if you talk about CBR of the material. The R-squared value goes up to 0.66, 0.7, around those sort of numbers. So we're starting to get to the right way of looking at it. But what is quite clear is that if you use one generic type, so whether it be a material from manufacturer A, you just test manufacturer A's material, you can get very good correlation between CBR results and protection performance. But as soon as you change from supplier or manufacturer A to manufacturer B, you can't use those same criteria. So you really need to understand what you're testing, and you need to test with the materials that you're going to use on site. The other big thing is needle-free. None of what we're talking about here is of any value if your geotextile is full of needles. And the number of times we see geotextiles come in for liner protection and it's got needles in it, it's phenomenal. If you've got needles in it, it doesn't matter how much strain you put in. You can put 0% strain in it, but if you've got needles in it, you're punching holes all the way through your HDPE liner. If the certifier can't, or the supplier can't certify needle-free, don't use it. Use somebody that can specify needle-free materials, and teach your guys on site to look for this sort of thing. We had a project recently where a geotextile was supplied full of needles to us. And I went back to them, I said, look, you've got needles all through your protection geotextile. The engineer went back to his site guy, said, yeah, there were lots of it, but we just pulled them out before we sent them to you so that they wouldn't hurt people, without understanding what the geotextile was supposed to be doing. So be aware of those sort of things. So, in conclusions, the method used for testing this strain values in a geomembrane will influence the strain values reported. You as designers or end users need to understand those differences. The lower the strain achieved makes that difference lower, essentially. So whether you're using the the European method or the laser scanning method, if your strains are less than 1%, it's not going to make any difference. In the USA, they've been using HDP for 37 odd years. And we've been doing some recent testing for America with typical geotextiles used in America and typical loads that they use. And strains are around the 11 to 15%. There are no documented failures due to stress crack resistance in America at this stage. That's not to say there's no failures, but there's no documented failures. So while I don't agree with their puncture resistance things, perhaps going down to less than 1% strain is overly conservative. At the same time, in stress crack resistance, when these specifications were first developed, so the German method that put a maximum incremental strain of 3%, when that was developed, the stress crack resistance of the geomembrane was set at 200 hours. Now the standard is 400 to 500 hours. So we're talking about 2 to 2.5 times more stress crack resistance, and yet I'm seeing trends pushing those strains lower and lower at the same time. So there's a conflict somewhere there. What you have to realize from a practical point of view is there's only so much protection a geotextile can give. We are now starting to push into, with going to less than 3% strains, that the only protection you will be able to provide to your geomembrane is sand protection. And don't think about putting sand down at less than 150 mils thick. It just doesn't work. You're more likely to damage your geomembrane with the loader putting a blade through your geomembrane in that process. So just from a practical point of view, be aware of that. So this is the end of the presentation. I'm nearly spot on my time. The magic numbers, and all I can say is I think the German standards are pretty good in terms of limiting strain. What we have to do is look at the different test methods and the different setups and apply factors to those numbers. So if we assume that the European method with the 0.25 as an average over the entire indentation and a 3% at a 3mm spacing is correct and acceptable, if we use the modified ASTM using the laser scanning technique with 1mm spacing, that we can increase that strain to 3.75% with an allowable 0.5% moving for the 1mm spacing, another 0.5% allowing for more realistic subgrade, a clay subgrade versus a rubber subgrade, and then potentially taking a 0.25% off because we're only testing it for 24 hours, not 100 hours. So you'll end up with a 3.75% strain. If you were going inverted where there's no subgrade involved, then you can increase that to 5.5% with 1.5% allowed for no subgrade, the 0.5% for the 1mm spacing, and then adding on another 0.25% because we only run it for 24 hours. So that's probably the most contentious part of the presentation that I'm doing today. And look, this is my opinion. I might be wrong, but it's somewhere to start with. And I think it's something that the industry needs to agree on and something needs to be discussed along the way. So I'm pretty much spot on time. Thanks very much for your time. I understand I've got a few minutes to talk about TRI, but just to let you know, TRI is a geosynthetics specialist testing facility. That's all we do. We only test geosynthetics. We don't test anything else. Our main focus is geosynthetics. It's what we specialize in. We have offices. We have 3 facilities in the US. We have a facility in Brazil. We have 1 in China and then 1 in Australia. So in terms of coverage on geosynthetics, we cover all the geosynthetics testing that are out there, and we certainly can give advice and input along the way if you needed something like that. So thanks again for your time, and if you have any questions, fire away.
Cool. Thanks a lot, Warren. Very interesting presentation. I'm just going to quickly look at Q&A section. So a question about recording. Yes, we recorded the webinar. We do record all of the webinars and we put it on our website. I can probably try and quickly show where on our website they are normally placed. So you just go ACIGS.org, that's our website. And then down here, there's a resources section tab. And then you just go to video library. And in there, we have not only the webinars, but also all of the seminars that we have recorded from the events that we have had this year. And we put all the videos in here that you can watch in your own time. Back to, yeah. So the question, based on the graphs you presented, Warren, which parameter you suggest for CQA? Is it CBR instead of mass? Is it the right move?
Look, I think CBR, if you know what geotextile that you've used, I think you have to do the testing to see which one works. And then from a CQA point of view, you can use the CBR to define whether the material is the same material as you've used for your testing initially. So, yes.
Okay, is it possible to get a copy of the presentation? Like I said, we put the recording on our website, but it's depending on the presenters if they would like to share the presentation with you. That could be also possible.
I mean, if someone wants to email, I can email a PDF copy. That's the easiest way.
Sure.
If they want. Yeah.
Just email Warren at TRI, and you'll get that. Yeah, I think that's what we have time for today. Thanks a lot, Warren, for interesting presentation. So we have already arranged for our December webinar, which is going to be on the 10th of December. Professor Tim Stark is going to talk about geomembranes mainly, and you will get the notifications pretty soon with the links to access the webinar. That's what we have time for today. Thanks a lot, everyone. Thanks for attending and listening to our presentation. And I'll see you next time. Thank you. You talk too much and then you run out of steam. Well, you run out of time at the end. That's the problem.